Welcome, everyone. We're just gonna give a moment for more people to join us. Okay, we'll get started. My name is Isabel Lee, and I work with Maura Lavelle and Izzy Chamber within the skin sensitization endpoint. And today I'll talk about new approach methodologies and how we use them for potency assessment within the skin sensitization group. And you can ask questions during the presentation using the question or chat function. And we'll try to get to as many of them as possible during this session, but we're going to also have a breakout session after this. So we encourage you to join us there, and any questions that we wouldn't have covered here, we're going to answer, and we'll have our collaborators that I'll introduce during the presentation that we can ask questions to. And yeah, I look forward to our discussion during the breakout session. And the way to find it is to go to the agenda, and you'll find in the events section the same titled session for the breakout. Okay, let's get started. So I'll start by introducing us to the skin sensitization program. It is divided into two. You have the safety assessment and the research programs, and these two work hand in hand. So when we have questions within the safety assessment program, we answer them within the research, and within the safety assessment program, we are writing safety assessments on discrete materials and natural complex substances. And with the research, we do work like looking at the quantitative risk assessment methods or potency assessment. So to look at what we're going to focus on today, the new approach methodologies or NAMs, we are actively using them in the safety assessment program. But then our goal for research on this side of things is really to refine the NAMs to make sure that they fit our purposes for safety assessments of fragrance ingredients. So we refine them within the research and apply them to safety assessment. As most of you are familiar with the skin sensitization adverse outcome pathway, a lot of the NAMs have been developed based on this pathway, and I'll just give a short summary. So the pathway is made up of two phases. You have the induction phase and the elicitation phase. The induction phase starts with the penetration of a small electrophilic chemical through the skin epidermis, where it binds to skin protein covalently, resulting in the activation of keratinocytes and dendritic cells. And these then signal to the T cells in the local lymph node to result in the proliferation, the activation and the proliferation. And then this concludes the induction phase, which is followed by the elicitation phase that results from a re-exposure to a particular chemical. And the way the situation presents is it presents as allergic contact dermatitis. So to start with the safety assessment program, what are we doing? We look at all available data for a particular material in order to make conclusions about it. And with the data, we look at hazard assessment. And then after hazard assessment, we want to characterize the potency of the hazard. So if a material is a sensitizer or a non-sensitizer, then we want to know for the sensitizer how strong it is, followed by risk assessment. So to dive in a little more, we start by looking at all available quality data. So we have a standard protocol for the confirmation of no induction in human studies, or HRIPT for confirmation of no induction. And then we have OECD guidelines. We do not do any animal testing, but we do have some historical data that we analyze based on OECD guidelines, and then we have OECD in vitro guidelines that we're using, and we'll introduce them today. And then we have the OECD toolbox and other in silico tools. And the goal here is to characterize data and determine if it's sufficient to determine whether material is a non-sensitizer. And if it is a non-sensitizer, that usually is the end of a safety assessment. However, if we find that the material is sensitizing, then we need to determine its potency in order to inform on a point of departure for quantitative risk assessment, which we also recently updated. So we can do quantitative risk assessment based on a CNIH, like I introduced, or we can also do it based on historical LNA EC3 or new approach methodology points of departure. And I'll talk about some of them today. So that's when we have a complete data set. But if we do not have a complete data set, then the next step is to look at whether we have any analogs, structural analogs that we could use to fill in data gaps for a particular material. And if we find that we do have analogs, then we go back to analyzing the data in this way, like I just introduced. However, if we don't, then the next step is to look at the dermal sensitization threshold, which is a similar concept to the threshold for toxicological concern. However, the DSC is focused on the skin. And the idea is to look at whether the current use levels of fragrance materials are below the DST. And if they are, then we do the quantitative risk assessment based on the DST. If not, then we do some data filling or bridging studies and using integrated testing strategies. And specifically, we look at in vitro data. And every 5 years, we do a reassessment to make sure that our safety assessments maintain the quality of the current scientific standards. And then another goal is also to make sure that the exposure levels that were being reported 5 years ago can still be supported, or if we need to do further analysis. So the focus of today is potency assessment, and specifically using the in vitro methods. So I'm going to jump into that a little more. So recently we published a database of fragrance ingredients, 106 fragrance ingredients. And the goal of this database was to provide a basis on which we would be able to do some work for in vitro analysis or other NAMs, and to see how they apply to skin sensitization and for the fragrance ingredient inventory. And what we did was to look at all available data. So historical animal data, human data, historical human data, and new and historical in vitro data, and other in silico data, to provide a weight of evidence for skin sensitization potency assessment. And after looking at all of these data, the 106 materials were categorized as either being extreme, strong, moderate, weak, very weak, or non-sensitizers, based on the dose ranges that we have here. So today, based on the data set that I just introduced, I'm going to talk about 3 pieces of research that we've been doing. So integrated in vitro regression models, and these are based on OECD guideline models that were developed by Javidan, Andreas Nash, and we're collaborating with Cindy Ryan and Frank Garbrick on this work as well. And then we'll also talk about the GARD skin dose response assay that was developed by Sensitization, and we're collaborating with them and IFF to look at the accuracy and reproducibility of the GARD skin dose response assay, and then also expanding the data set. And then lastly, I'll also talk about a project that we initiated as a request from the expert panel for fragrance safety, looking at the potential for vinyl and vinylines in skin sensitization. And then there are more projects and collaborations that we're working on, and I'll introduce those two at the end. So let's jump into looking at the point of departure derivation using OECD in vitro methods. So most of you are probably familiar with, the OECD LP, like I just introduced, and the in vitro methods that have been developed based on the adverse outcome pathway. And Andreas Nash took these in vitro methods, so the kinetic DPRA, looking at key event 1, the keratinescence assay, looking at key event 2, the H-CLAT assay, looking at key event 3, and combined them in vitro models, specifically their quantitative data, and combined them to result in 5 different equations for predicting an LNA EC3. And that has been very helpful for an initial assessment for a point of departure. And then another recently produced work, still by Andreas Nash, was the human potency value assessment, and it's based on the same in vitro methods, resulting in 5 different equations as well, and these are marked by the letters D and E. So with the data set that I introduced before, what we did was to take all of the quantitative data from the kinetic DPRA, keratinescence, and H-CLAT and input it into Andreas's models. And what's great about these models too is there's an Excel spreadsheet where you can enter as many materials as you'd like and their data and give you an output. So we did that for 100 materials, and here's an example. We have cinnamaldehyde, where we generated different EC3 values in percentage based on the different equations. And then also based on the more recent equations, you have the human potency values that were also predicted in the percentage form. So we did this for 100 materials. However, only 62 of these materials were we able to compare, satisfactorily the output from the 5 equations. So we have the 5 equations from the EC3 and the 5 equations from the human potency value. So we decided to focus on these 62 materials so we could compare the equations and see how they performed. The good thing about the 62 materials is that we had the same distributions of the reactivity alerts as you'd see within other fragrance ingredients. So you have the Michael addition, shift base, you have a lot of the other materials that didn't have any reactivity alerts. However, when you looked at their metabolites, you see that a number of them had been predicted to be weak sensitizers or strong sensitizers, and still a number were non-sensitizers. So this was a great subset of materials to move forward with anyway. Another area of variability was also within the amount of weight of evidence potency categories that we got. So we had strong, moderate, weak, and very weak, and also non-sensitizers represented within the data set, which was also great. And as you can appreciate here, most of them were weak or very weak sensitizers, which is very similar to what we see within the fragrant ingredient inventory. So to jump into the data, on the left-hand side are the potency categories, followed by the weight of evidence potency, the reference potencies, and the numbers are the number of materials that are predicted within that category. For example, weak were 30 reference materials fell within the weak category, and the very weak had 21 materials. And followed with this, you see the EC3 predictions for the 5 equations, and you see the potency value predictions for the 5 equations. And one thing we wanted to highlight here is that you see that the very weak and weak materials are very well predicted using both sets of equations. And then to jump into the data a little more, I'm going to present equation 1. and 1D. And these are the equations for EC3 prediction and human potency prediction that combine the keratosenescence assay and the kinetic DPRA assay. And going down is the reference data set, and going across is the predictions from the equation. And in the middle here is where you had exact matching of the predictions of weight of evidence categories, and then off to the side are categories that were off by 1, and so on and so forth. But something to appreciate here is that 43% of the materials for those predicting the EC3 were within the exact match, and 45% were off just by 1 category. And so in combination, you see that about 88% of the materials were captured within a good accuracy of prediction. And then this here is the human potency value prediction equations, and you have an increase to 50% of materials being predicted within the exact matching category, and 41% being off only by 1 category. And so 91% of the materials were captured, which was also pretty good. So the other equation I wanted to share, we have data on all of the equations, but I'm only sharing a few here to save time. But then there's the equations that are combining the keratosenescence, kinetic DPRA, and H-CLAT assays. And as you can appreciate here, you see you still capture 88% of all the materials using the EC3 equation. And then when you use the human potency equation, you are capturing 89% of all of the materials, which is still pretty reasonable. So whether you're only using the keratosenescence assay with kinetic DPRA, or combining keratosenescence assay, kinetic DPRA, and H-CLAT, you're still getting a pretty decent prediction of human potency categories. Another assessment we did was to look at the fold changes between the predicted numbers versus the reference numbers. And we did this for all of the 5 equations. And presented here is those looking at the human potency value. And what we saw was that there was a low difference between all of them. So we had a median fold misprediction ranging from 1.7 to 3.4, which is a good performance that we see for a lot of these NAMs. And then when you look at the EC3, the median fold misprediction was between 1.8 and 2.5, which is slightly lower than what we saw with human potency values, which is also still a good prediction. So conclusions for this project: we saw a distribution of predicted potency categories being similar to that of the weight of evidence categories, and as expected, we didn't see any extreme sensitization being predicted. And then both equations looking at EC3 or human potency values provide a good point of departure for risk assessment. And equations 1 and 1D, so those combining the keratosenescence assay and the kinetic DPRA, provided the highest prediction accuracy for weight of evidence categories. And the median fold misprediction for the human potency value was between 1.7 and 3.4 for all of the 5 equations. However, that for the EC3 was between 1.8 and 2.5 for the equations. So just to get into the second assessment, so the guard skin dose response assay that we are working on with Sensitization and RIFM. So you're all probably familiar with the guard skin assay. This was recently introduced into the OECD guideline 442E. And it looks at, the dendritic cell activation. but there's a modification of the assay that focuses on looking at a continuous potency assessment. And this is great because it actually provides a point of departure that can be used for quantitative risk assessment for dermal sensitization. And the way the assay is performed is you have simulations in a titrated range. So about 6 different doses are tested, and then the guard skin protocol is applied to generate decision values. And then the next step is to plot the guard skin dose response decision values against the concentration values. And this is to generate a CDV0. And the CDV0 estimates the lowest concentration required to induce a positive classification. And the third step is to use the CDV0 values as input into linear regression models to predict points of departure, such as the LNA EC3, the human NOEL, but you can also predict something that I'm about to introduce, which is the composite potency value. So our first assessment was to look at the assay and how it predicts for fragrance ingredients. And what we found with this number of fragrance ingredients was that it correlated really well with the reference data set with a Pearson correlation factor of 0.73. And then the next step was to look at the reproducibility of the study. So 3 sets of experiments that were done blinded on about 17 materials. And what we found was that about a very good reproducibility for the predicted NOEL or the predicted LNA EC3 in the 3 experiments. It was highly reproducible. But then the question comes up, should the model predict human NOEL or NESO or the LNA EC3? And so, for example, for cinnamaldehyde, these are the numbers you get in dose per unit area for the LNA EC3 and the human NESO. And you can see that both references are pretty much predicting the same thing. They're informing on the same phenomenon, which is the skin sensitization potency. And neither is perfect. They're both associated with measurement errors. So this is where this question of maybe having a composite value that takes into account the LNA EC3 prediction, human EC3 prediction, will be helpful to only get one continuous potency value that is units that are useful for skin sensitization, which is micrograms per centimeter squared. So we have Andy from Sensigen is going to join us and will provide more detail on the composite model. But the message about the model is that it is created from looking at both the human LNA the human NOEL and the LNA EC3 and comparing those values to CDV zeros to predict a value. And the model is simple and only contains one parameter. So we'll go into more detail during our breakout session, which we encourage you to join. So we ended up testing 100 unique materials from the first 2 pilots just to see how the assay performs for fragrance ingredients. We had some data, and then we have the reproducibility study that I just talked about, and then we extended the pilot with 65 materials. So we ended up testing 100 materials from that initial data set that I introduced. So here is a heat map showing the data and how it came out, specifically looking at the prediction of the potency values. So on the y-axis, you see the predictions, and on the x-axis, you see the reference values. And in the middle is where the two actually had a concordance or matching. So there was a total accuracy of 31%, so all of the materials matching, and approximate accuracy of 81%. So if you take into account those were in the middle and those that were off by just one category. So it was a decent prediction as well. However, we also noticed that the very weak range was generally not very well predicted. And we came up with a hypothesis that maybe the guard skin dose response assay is a potency predictor for potency, but the resolution for the current model is not sufficient due to maybe limitations of the reference data set, or maybe the guard skin assay itself. So to test this hypothesis, we decided to combine the weak and very weak ranges for the predicted values and the reference data set. And what we observed was that the total accuracy increased to 53% and the approximate accuracy increased to 98%. So about 98% of all of the materials were captured within this prediction model, meaning that we maybe have a little bit of work to do to answer for the very weak range of prediction for this model. So conclusions: the guard skin dose response assay predicted human NOELs very well with Pearson correlation factor 0.73. And then the predicted NOELs and LNA EC3 values for the blinded study were highly reproducible. And the composite potency was designed to account for the shared variance between the predicted NOEL and the EC3 values. And we observed an approximate accuracy of 81% and actually what I didn't say was that whenever we had mispredictions, they were mostly over-classified. Another observation we made was that when the weak and very weak ranges were combined, that the approximate accuracy increased to 98%. And the final project I'm going to talk about is how we analyze the sensitization potential of vinyl and vinylene compounds using the Census assay. And as I said, this was a question that came from the expert panel for fragrance safety when we were looking at the read across and how, to determine that for materials containing the vinyl and vinylene functionalities. So when we started looking at this work, we went into the fragrance ingredient inventory and found that about 1,300 materials contain this vinylene functionality, but we only had data on about half of them, and a few of them had enough data where we could do hazard assessment. So that's determining whether the materials are non-sensitizers or sensitizers. And there was a mixed data set. You had 68 non-sensitizers and 217 sensitizers, and some of them we could do quantitative risk assessment for, and some we couldn't. So as I just stated, the data was a mixed bag. You had positive data and negative data. And this was primarily because of the mixed bag nature of the data set we looked at. We're looking at historical data. So we had guinea pig maximization tests, Bueller test, local lymph node data, human maximization data, confirmation of no induction in humans, and in vitro data. So that's what caused the data on the unsaturated materials to, provide the inconclusive results. And so to better compare the materials, we decided that maybe we should look at one study type in order to do an apples to apples comparison, and also make sure that the materials that are being tested are curated, that we are testing materials that would inform on how the unsaturations are acting in skin sensitization. And we decided to go with the census assay because we'd recently done some work and published it looking at how it performs for fragrance ingredients. And we assessed 174 fragrance ingredients and found that about 85% of them were very well predicted for their potency. And we came to the conclusion that the census assay provides a good approximation for the skin sensitization potency assessment. And another question too is, are you looking at the irritation or actual sensitization? So that's another advantage of the census assay, because it could distinguish between these two. And so we decided to go with it. And just to introduce you to the assay, it's conducted on the human reconstructed epidermis, the episkin. And the advantage of episkin too is that it's been shown to have some of the enzymes that would be essential for metabolizing vinyl and vinylene functionalities. And specifically, we're looking at the cytochrome P450 enzymes. So the way the assay works is the test substance is exposed to the episkin and then incubated for 15 minutes, after which it's washed and the substance removed and allowed for post-incubation for 6 hours, and then the tissue is lysed, cDNA extracted, and RT-PCR conducted on 61 biomarkers that are quantified for irritation and sensitization. So, as I just mentioned, the census assay can distinguish between irritation and sensitization. And if you have 20 or more genes overexpressed, the sample is rejected and the chemical tested at a lower concentration. So if 20 genes are significantly induced, the data is concluded as being inconclusive because you just have too much irritation. Then a molecule is classified as being positive if at least 7 out of 17 antioxidant response element genes, or ARE genes, are expressed, and or if 7 out of 21 of what's categorized as the census genes are significantly induced. Then the lowest test chemical concentration fulfilling these criteria is used for potency classification. For example, materials quantified as being an extreme sensitizer if the induction is at 0.1%, positive at 1% is strong, 10% is moderate, and 50% is weak. If all tested concentrations are negative, then it's considered to be a non-sensitizer. So on the curated data set, we had unsaturated materials that contained the vinylenes and the vinyl groups that were tested along with their saturated counterparts. So for example, here you have citronello that had dimethyl 1-octanol as its counterpart, hex 3-enol acetate with hexyl acetate as its counterpart, and estragol with propyl anosol as its counterpart. And we ended up testing 30 materials in total. And overall, what we observed was that we didn't have any strong or extreme sensitization from the saturated or unsaturated materials tested. So these would have the potencies in these categories here. What we observed was that most of them were in the non-sensitizer very weak and weak ranges. And then I'm going to also talk about those that were predicted to be moderate, which we also came up with a rule for. Another general observation was that most of the materials had some form of irritation. So about 50% of them had mild irritation, which was 7 to 15 irritation genes being upregulated, and 43% had high irritation, which was greater than 15% of 15 irritation genes being upregulated. So as I mentioned, we came up with a rule for moderate sensitization. And these are examples of materials that were categorized as being moderate within the census assay. And the main observation we made was that whenever we had this type of conjugation of the unsaturated bonds, is where we had moderate sensitization. So you have either the upregulation of ARE genes or census genes. And we had some historical data to also look at, and only this one material was a non-sensitizer. You're looking at the historical data, but the others had some historical data indicating them to be sensitizing. So we came up with this rule for moderate sensitization for the vinyl or vinylene containing compounds. The double bond conjugation is very important. So in conclusion, no extreme or strong sensitization was observed in this study. And then mild to high irritation was observed. Most of the fragrance ingredients that were tested in the census assay. And then most of the saturated controls were either non-sensitizers or very weak sensitizers. And for most of the unsaturated ones were non-sensitizers, very weak or weak in census. And whenever we had moderate sensitization, we could explain it using the double bond conjugation rule. So this is a rule that we're going to continue to apply in our safety assessment program. So this is an example where we've done an assessment using our research, and we're feeding it back into our safety assessment program. Then to conclude, like I mentioned, we have some other studies that we're doing in collaboration with our members and others. And so we welcome collaboration. We have a collaboration with P&G looking at the peroxidase peptide reactivity assay, or the PPRA assay, and how it can characterize reactivity for pre and prohaptins. We also have a study in collaboration with Givaudan looking at all available data for materials that have been predicted to have high historical LNA EC3s, because we suspect that these data might be maybe an artifact of them having not been evaluated for the OECD guidelines. So look forward for those results. And then we have another study looking at the utility of the Bayesian network model for modeling skin sensitization potency. And then another update that we're making is on the CNIH protocol, and we are working on a manuscript on that, so look forward for it. But yes, thank you so much for joining us today, and I thank you for listening, and please join us in the breakout session. And I would also like to thank my colleagues Mara and Izzy for working on this, and we're always available for collaboration, so please reach out to us if you have any work that you'd like to do together, if you have any other questions. Thank you.